Okay, I would like to do an example with you folks of motion in one dimension and using graphs to solve the problem. Now here's an example, and just to expand on what we did in class on Friday. Suppose, let me get my pen working. Suppose we have an individual on a branch, and he throws something down at 5 meters per second, and it hits the ground. And suppose when it leaves his hand, it's t equals 0, and when it strikes the ground, it's 3 seconds later. And we'll call this distance here, call that our distance traveled, our displacement, delta x. And can actually call this spot right here x equals 0. So down here is really the value x, and delta x is x minus 0. And what we'd like to find is delta x. And I want to show you how you can do that, do another example of how you can do that using graphs. Let's draw our velocity versus time graph. Time in seconds, velocity in meters per second. Now let's call down positive. We're allowed to do that. And the acceleration due to gravity is down also. So the object starts at positive 5 meters per second because I called down positive, and it will continue to speed up in the positive direction. So we will have a graph that looks like this, where right here is 5 meters per second, and this area here is 0, 0, and right here we'll call this 3 seconds. And we can also draw the acceleration versus time graph. And again, acceleration is positive, so it's up here. Again, this is time in seconds. This acceleration in meters per second squared. And this is 9.8. And we can kind of identify in here where 3 seconds is. Don't mind this little line here. I don't have an easy way to erase right now. So there we've drawn two graphs that are modeling what is going on. And we want to figure out what delta x is. Now one of the things that you know is that this area bounded by the velocity versus time graph, that is delta x. Because the area, the physical meaning of the area of a bounded by velocity versus time graph over the time of interest is the displacement. Now we can break this up into two geometric figures that we are familiar with. Basically a rectangle and a triangle here. So we can write that delta x is equal to the rectangular area is basically length times width. So here's the length area, 3 seconds, times the height, which is 5 meters per second. Notice the units work out to give you something in meters, plus now the triangle. It's going to be 1/2 base 3 seconds times the height. And here's something interesting. The height is some velocity that we don't actually know right now. I'll call v final. So it's going to be v final minus 5 meters per second. Now, unfortunately, we can't solve for delta x because we don't know this guy. But let's see if the acceleration versus time graph can help us. One thing we know that the area bounded by the acceleration versus time graph, that is delta V, change in velocity. And in this case, it must be V final minus 5 meters per second by definition. And if we look at the area, we also have it equal to 3 seconds multiplied by the height, which is 9.8 meters per second squared. So this part here comes out of this part here. That's the area. And this is just the definition of delta V. It's the final velocity, which is the velocity at 3 seconds. And this here, the 5 meters per second, is the velocity at t equals 0. Now this is kind of neat. Notice that this appears there. And since this is equal to that, we can put this in there. So let's write our delta x equation again. It's going to be, we can actually drop, cancel out the seconds up here, and we can have 3 times 5 meters plus 1/2 3 seconds multiply, again, this guy, V final, minus 5 meters per second is just equal to this. So it's going to be 3 seconds times 9.8 meters per second squared. And notice the seconds, 2 of them here, 2 of them there, and you're left with meters. So we have 15 meters plus 3 times 3 is 9, and there's a 2 from the 1/2, multiplied by 9.8. And I'll leave it, I actually don't have a calculator right in front of me. There you go. I'm trying to make a fat equal sign, and it's looking kind of funny. But you're going to have 15 meters, this is going to be meters, plus 9 times 9, it's about 81 divided by 2, so somewhere around 40. So it's going to be 40 plus 15. So it looks like 9 9's 81 is 40. Looks like it's about 55 meters is the answer to that. And that's how you do that. All right, I hope that is helpful to at least some of you. You can use the same techniques when you do the runner problem.